Hello, Leo here. We're gonna do another video on our vector function. So we've been talking about derivatives a bit. Let's talk about integrals. So as far as computing them, it is every bit as straightforward as we could hope. Let's suppose I have a vector function. Oops. Let's draw. Let's suppose I have a vector function. V of t is equal to x of t, y of t, z of t, and I want to integrate over this. Well, let's say I'm integrating over an interval. Oops, there we go. Dt. Just like with derivatives, if you go through the process of taking the limits, thinking about a Riemann sums, and doing a similar type of thing here, little intervals of increments of t times the vector function itself, and just use the definitions, the way it works out is you can integrate over each of the component functions over the same interval, right? Which is an ugly looking thing, but just like with derivatives, what it really means is when I'm asking you to take an integral, if you're asked to take an integral of a vector function, it just means you've got to do 3 integrals or 2 integrals or 10 integrals, depending on how many, what space you're working in and how many components you have. Right? But the process is the same because now these are all just real value functions. So these are just our regular old integrals. Any rules you use to solve them, you can use that you used to solve real valued integrals previously, you can use on these. You know, it's just a process of organizing. If these are complicated, I of course would do them, you know, take their own space to do each one. We also get from this that we can write this as, oops, wait, sorry, I'm just change my notation. Just changing what I call things. So just like the fundamental theorem of calculus, we can evaluate these by taking the value of the function, the vector function on the endpoints and finding the difference. This is with the implication that r prime of t equals v of t. In other words, r is an antiderivative of v, right? So it's exactly how we formulate that for real valued functions. They're just vector valued functions, okay? So let's use this opportunity. We're going to do an example in just a second. Let's use this opportunity to maybe give some meaning to this whole thing. Let's suppose r of t, let's suppose r of t is a position function. Position function for some particle, okay? Well, we know that r prime of t is approximately r of t plus h minus r of t over h, right? I'm just using the limit definition, but without the limit, just saying this would be an approximation. What is it that we have here? Well, if I'm looking at a picture of this, right? Let's call this the origin. Maybe this is r of t, and this is r of t plus h. Then this thing on top, the numerator of this difference is r of t plus h minus r of t. This is a displacement vector over the interval t plus h, right? In other words, it's a vector that points from where it was at the beginning of the interval to where it was at the end. So it's this displacement vector. Let's put vector in there. Okay, over that interval. right? Well, when we divide by h, remember h is something we're putting in as a t value, right? It's our input value, and this is a function, if this is a position function where our inputs are time, h is a time, is in units of time, we're getting displacement vectors per unit time, right? So let's write this. This is going to be displacement per unit time, right? It's just like velocity, but it's coming in the form of a vector, okay? So each individual component is the displacement in the x coordinate per unit time, the displacement in the y coordinate per unit time. And what we get is displacement per unit time. And this is where this idea that this derivative of r, of a position vector, is our velocity vector because of this idea of displacement over time, which is why I used v up here, right? It also gives meaning to what's going on here. With all of this in mind, right, let's look in more detail at this, right? Then we're integrating over the velocity vector, we get our displacement, right? Displacement vector, right? So if we have velocity vectors for, you know, it's telling us in what direction and how fast we're traveling at each moment over this interval. If we add up all those instantaneous velocity vectors, that should tell us how far we've traveled in over that whole interval, right? This is from where, how far and in what direction, I should say, because we're adding up the directions and the magnitudes, right? This stuff is all kind of coupled together in these vectors. So this is the displacement vector over the interval AB, right? Just like we had in the numerator of our derivative over here, right? So it's that's how these things are related to each other, okay? So that's one way to get a little intuition about what antiderivatives or integrals might mean in this context, right? Because what we'll find too is that we have the same relationship we've seen in Calc 1, where we have a position vector. We're going to do more work on this in some later videos, but our prime of t will be the velocity vector, and then our double prime of t, which is the derivative of velocity, is going to be the acceleration, right? And so we have the same relationship we saw in previous calculus classes or videos, as we move in this direction by taking derivatives, and we move in this direction by taking antiderivatives, right? If you start with an acceleration, you want a velocity, you can take the antiderivative. We get some ambiguity there with those constants of integration, but it's still a nice parallel, these two relationships. Okay, so let's do an example of this and then look at a graph of it. So I will clear some space. Or let's just go to a new page. Okay, so let's say I have the function v of t is equal to negative sine t cosine t 1. Let's take an antiderivative, okay? So here, I'm not going to integrate it over bounds yet, right? And we'll use the same idea that we just talked about for definite integrals. I can just take the antiderivative, the indefinite integral of each component function. Right, so what happens here? An antiderivative of negative sine is going to be cosine of t, but we get a constant of integration. I'm going to call it c1. Here, my antiderivative of cosine is sine of t, but I get a constant of integration. I'm going to call it c2, right? They might be different, so I want to distinguish between the two. And then the antiderivative of 1 is t, and we get a third constant of integration, which we can just rewrite this as, which we usually shorthand as the vector c, right? So just like you get that constant of integration for real valued functions as we did above here, we can think of it as one big constant, but it has three components, right? And so remember what this means, right? This antiderivative. So if we're, from the discussion we just had, this antiderivative should be giving us our position function. Well, the function we have can tell us the relative position, but we need to know where we're starting from. We don't know the starting position if we have all the velocities, right? If I tell you I travel, 200 miles per, 20 miles per hour for 3 hours, you know I've traveled 60 miles, but you don't know where I am because you don't know where I started from. Okay. So let's turn this into let's now do this with a. Sorry, let me say one more thing before we do the next step. This piece of this, remember, is one we've looked at before. This was our corkscrew spiral traveling up the z-axis, right? The y, x and y coordinates just give us a unit circle, and the z component is just increasing as we rotate around that circle. So if this was the z-axis, this was the graph that looked like that. We'll go to a nicer picture in a moment, but I'll just remind you of that. Let's take a definite integral of this. I wanted to do the right. So I now have an antiderivative. Notice r prime would be v of t. So that fundamental theorem that we mentioned a moment ago looks like this. So what's r of pi? That's going to be cosine of pi, sine of pi, pi, and I've got the vector plus the vector c, and then I can subtract cosine of 0, sine of 0, 0 plus c. Right? But the same thing happens when we do antiderivatives and then definite integrals in real valued functions. We don't really need to keep this constant of integration because we see we're going to get a plus c here and a minus c here. So those are going to go away. And what we're going to be left with is, let's see, cosine of pi is -1, sine of pi is 0, and we've got pi. And then I'll have cosine of 0 is 1, sine of 0 is 0, 0. So what do we get? We've got -2, 0, pi. Okay. So what is this telling us? It's telling us that this position vector r of t has moved from in the interval 0 to pi. It has moved in a direction of -2, 0, pi. Right. If we drew this vector, right. So let's maybe say it this way. If this is the vector r of 0, and a little later we get r of pi pointing at our new position, this vector in between is going to be -2, 0, pi, right? That's how, it doesn't matter what we did in that time, right? We know it's some piece of a corkscrew, so I don't know if I've drawn this accurately, right? Maybe it wound around. I mean, we can do some work to figure out, and we're going to look at it in a moment. I know it hasn't actually gone around several times because we've only gone half a rotation. But in any event, I don't know exactly how it got there, but I know that this is where it started and this is where it finished. So its displacement vector over that interval of time is this one we just computed. Okay. All right, let's take a better look at this situation. Let's go to GeoGebra. All right, so here's that familiar graph we've looked at several times. Okay. Some things out of the way. So right now we're just looking at we're just looking at the graph itself. Let's add some things in. Oh, I've got a particle traveling along it if we think about, so this is just traveling from 0 to pi. So again, we can see where our, let's zoom in a little bit, where our particle starts is at the point 1, 0, 0. Right, so the red axis is the x-axis, the green is the y, and the z is blue. So we're at 1, 0, 0, and we move for a while until we get to this point at the end. Oh, it doesn't let me actually put in pi. It says pi, but I notice it's only at 3.1. So it's not quite where I think it is. It should be at -1, 0 pi. It's not quite there because this won't let me go, but it's a pretty good approximation right there, right? So let's look at some of our vectors. Here is the position vector, the vector function r of t, right? Points at, I can go even a little closer. Okay, so that's pointing out where we're at. Let's add the velocity vector. So as we travel, right, this velocity vector is the whole time pointing in that tangent direction, right? Well, we can think of that integral as if I added up all of these velocity vectors, right? We know how to add vectors. I wouldn't get precisely the displacement vector I want because it's an approximation, but I keep taking smaller and smaller intervals, right, to get better and better approximations. That's the same intuition here. I would get something pretty close, right? In the beginning here, it's pointing up, and moving in one direction, and as it moves around, we get different directions and so forth. But anyways, that's part of our intuition. And I shouldn't say these velocity vectors. We're multiplying them by some infinitesimally small, right? Because otherwise these are way too big. But in any event, that's the idea. There's our velocity vector, our position vector. Let's add something else in. Here is the vector in the beginning, right? So it's hard to see. There is a vector along that axis. Let's actually move the axes. Okay, so now the axes are gone. So that R0, R0 is the vector where we were at the beginning. Oops. R pi is the vector where we are at the end, right? So just where we end up. And then the displacement vector, that was the result of our integration, tells us exactly how far we moved, right? It doesn't take into account all these little twists and turns we make along the way, but it just tracks where we were in the beginning and where we are at the end of that interval, right? So this is the interval we tracked, went from 0 to pi, is just this little piece of the curve, and we were getting that displacement vector. Okay, so that I think is it. Maybe we'll take one more view from another direction. It's just sometimes neat to see these things, right? So there's our original position. We travel along this curve. We end up over there. And so that displacement vector I called D, that solid black one going across the middle, ignores all this curve that we're doing and just goes in the most direct route from where we started to where we finished. Okay, let's stop there. Thanks, everybody. I will see you next time.